Welcome to Yetimkhana and Madrasa, Anjuman Khairul Islam's Pune College of Art, Science and Commerce, Camp Pune 1. Myself, Dr. Arif Tamboli, working as Associate Professor in the Department of Electronic Science. Dear students, I welcome you all for the FY Electronic Science. So, in this video, today I am going to cover all about the basics of semiconductor electronic science. So in the beginning, I just wanted to record the face so that you will be aware about the teacher. And now I am going to close the face recording so that it will give a very easy and convenience for explaining all other parts. So now I am going to close the video and henceforth you can understand the slide presentations without this video. So in the beginning for the dialogue, establishing the dialogue, I have just turned this on. Thank you very much for this. So in this way here now, we are going to study the electronic science as one of the subject, and from University of Pune, that is Savitribai Phule Pune University. This is our syllabus for 2 credits and 36 lectures. Electronic science paper second, which I am teaching to you. There is one more paper, paper 1, and there is practical course also. So this EL112 is the code for that course. And as it is a semester pattern, you have only 3 chapters or 3 units in each course. So in our this course, unit number 1 is about PN junction diode, working, IV characteristics, formation of depletion layer, formation of barrier potential, forward and reverse bias conditions. And in this way here, you can understand that as far as this slide is concerned, as far as this chapter is concerned, the number of total lectures allotted are 40, and we are going to cover that in 14 lectures. Then here unit number 2 is also there, in which there is a bipolar junction transistor, field effect transistor, MOSFET, basics applications of that devices, and accordingly there are so many components and their IV characteristics and their applications you need to study. And this is unit number 3rd, in which there are light emitting diode symbol and use in CR circuit, and accordingly the devices are there. And in this way here, just go through the syllabus of Savitribai Phule Pune University for this, and you can understand that there are so many things to be studied. So now let us start our first chapter, and the first chapter, first unit is your PN junction diode. So here is the junction diode, PN junction diode. But before starting the PN junction diode, in today's lecture, I'm going to revise all your basics about the electronic science, that is the physics. In 12th standard, in the physics you have studied semiconductor, and from that semiconductor only the branch of electronic science starts. So here electronics materials are basically divided into 3 different categories, namely conductor, insulator and semiconductor. So all of you are aware about conductors. So here all metals, example copper, silver, gold, aluminium, nickel, and here the copper wires bundle is shown. And in this way here, all these conductors, all these metals are good conductors of heat as well as electricity. And why it is there, so that we are going to revise in short. Then next is your insulator. So insulators are bad conductor of heat and electricity. You are aware about that. And the examples of insulator is your glass, ceramic, plastic and wood. So photograph of wood is shown over here. And then third category of electronic materials is called as semiconductors. Is called as semiconductors. So here semiconductor materials examples are silicon, germanium, carbon, and here these are the pictures shown for the semiconductor materials. So now we are going to divide the materials into three categories through the frame of reference of electronic science as a conductor, insulator, and semiconductor. And today's lecture we are going to revise only all basics which you have already studied in 12th standard. But in that case, you have not given the attention to that semiconductor topic through the frame of reference of electronics, which we are going to take the care today. So here, read the things very carefully. It's very simple. All metals are good conductor of electricity, but the conductivity varies according to the electrons in the valence band. So electrons in the valence band means what? Electrons in the outermost shell, as well as according to the atomic number of metal. So conductivity of a metal is not only going to decided on the basis of number of electrons in the valence band, but it is also going to decided on the basis of what? Atomic number. So here I have taken some examples. Platinum, gold, silver, and copper is having one valence electron. One valence electron means only one electron in the outermost shell or orbit. And all these metals are good conductor of heat and electricity. All these metals are good conductor of heat and electricity. In this way, the platinum and gold is having the highest conductivity. The platinum and gold is having highest conductivity, and therefore that materials are very good conductor of electricity. So in this way, now let us go to the next slide. Due to large atomic number, due to large atomic number, the valence electron is far away from nuclei, and binding force between nucleus and that electron, which is in the valence band, it is said, and it is far away from the nuclei, and therefore binding force between nuclei and that electron is very less. Therefore this electron can be easily knocked out and forced into conduction as soon as external voltage, that is electric field, is applied to the metal. And in this way here, why the metals are called as very good conductor? Because in case of metals, because in case of metals, the valence electron is far away from the nuclei. The valence electron is far away from the nuclei, and it is very easy to detach that electron. It is very easy to knock out or detach the electron from valence band and force into the conduction band. So now let us see some examples. So here all of you know about the metals. Platinum. Platinum is also called as white gold. Platinum is also called as white gold. See, the atomic number of the platinum is 78. Atomic number of platinum is 78. And here you come to this electron configuration. Electron configuration. You will find out in the last orbit, very see carefully, there is only one electron here over here. And here it is given 1. So platinum's atomic number is very large. Therefore, the valence electron or electron in the outermost shell is far away from the nucleus. Is far away from the nucleus, and therefore it is said that the binding energy between the nucleus and that electron is very less, and therefore you can detach that electron just by connecting external voltage. Just by connecting external voltage. Now let's come to the next, gold. Gold is also a metal. Look at the atomic number of the gold, 79. And here you look at the electron configuration. Only one electron is there in the outermost shell. See here, only one electron there in the outermost shell. And the all other orbits are almost fulfilled. And here, next example is your silver, atomic number 47. And look at the electron configuration. Last orbit is having only one electron, see here, and that electron is shown over here at the top. Next is the copper. Look at the atomic number 29, and electron configuration is somewhat like this, and there is only one electron in the outermost shell. Now let us compare platinum and copper. Platinum is having atomic number 78, copper is having atomic number 29. and therefore the conductivity of a platinum is much more greater than the conductivity of the copper, because in case of platinum the electron in the outermost shell, which is called valence band, is far away from the nuclei as compared to the electron in the outermost shell of the copper, that is valence band of the copper. And therefore in case of platinum as well as gold, you can say, we can detach this electron or we can knock out this electron very easily by applying external voltage, and we don't have to waste any external energy in the form of electricity to knock out this electron. And therefore these two metals are very good conductor of heat as well as electricity, but we cannot offer them into the wirings at which is used in the home because they are very costly. Now let us go to the some other metals also, and there is one iron. Iron's atomic number is 26, but in case of iron the conductivity of iron is less as compared to your copper and all other metals which you have just studied. So look at the electron configuration. There are two electrons in the outermost shell, which is called valence electron. Here one is shown and here is one shown. And in this way, aluminium, look at the atomic number. So atomic number is 13, and here three electrons are there in the valence shell, that is the outermost shell. So aluminium's conductivity is less as compared to all others which you have studied. Nickel. Nickel is having only one electron in the outermost shell. So here nickel is there and it is also good conductor. Tungsten. Tungsten is used as a filament in what bulbs. So here tungsten's atomic number 74, but the valency is 2. Valency is 2 means what? Electrons in the outermost shells are 2. And in this way, you will understand that all metals are good conductor of heat and electricity. All metals are good conductor of heat and electricity. So here it is explained, all metals are good conductor of electricity, but the conductivity varies according to electrons in valence band, that is electrons in outermost shell, as well as according to atomic number of metal. The atomic number of platinum is large, therefore the valence electron is far away from nuclei. So platinum, gold, silver and copper is having one valence electron, and all these metals are good conductor of heat and electricity, but the highest conductivity is of platinum and gold due to large atomic number. So atomic number also matters, and not only valence electron. And here, due to large atomic number, the valence electron is far away from the nuclei, and binding force between nucleus and that electron is very less. Therefore, this electron can be easily knocked out and forced into conduction as soon as external voltage, that is electric field, is applied. And this is all about metals. One more thing you have to remember about the metal: when metal is heated, the resistance of metal increases, and therefore it is said that all metals are having positive temperature coefficient, that is PTC, positive temperature coefficient, because after some time we are going to deal with semiconductor, and in semiconductor exactly reverse. When you heat the semiconductor material, the resistance of semiconductor material decreases as temperature increases, and therefore it is said that semiconductors are having negative temperature coefficient. So we'll come to that. And in this way, this is your normally day-to-day life. We are using copper rods, copper cables in wiring and in all these things, because copper is very good conductor. Copper is very good conductor. The valency is only 1. Atomic number is 29. And now let us go to the basics of all 12 standard, which you already studied. What do we mean by the atom? So atom is a tiny particle. Atom is a tiny particle. So atom consists of what? Atom consists of nucleus. Atom consists of nucleus, and nucleus consists of protons and neutrons. Nucleus consists of protons and neutrons. Protons are positively charged charged. Protons are positively charged, and neutrons, as the name suggests, neutrons are neutral. There is no charge on neutron. And now in the atom there is a nucleus, and in the atom there are protons and there are neutrons. Protons are positively charged, To balance the number of protons which are positively charged, whatever the number of protons are there, that many number of electrons are there in atom. So atom is consist of nucleus, protons, neutrons, electrons. So I am going to show you the image or the photo of the atom. So in this way, in atom, at the center of the atom, that is the core, the nucleus is there, and nucleus consists of protons and neutrons. Protons are positive charge. So whatever number of protons are there, same number of electrons are there accommodated in the first orbit, second orbit, third orbit to balance the positive charge with the negative charge, and electrons are negative charge. So this is the structure of the atom, and we are going to see now the atom. So here atomic structure. So you can see here atomic structure. So in this atomic structure, you see very carefully, here it is called nucleus. Here it is a nucleus. Now inside this nucleus, as we studied in this table, see here nucleus. So inside this nucleus, there is what? Protons and neutrons. So inside this nucleus here, there is a proton. So protons are marked by positive charge, and there is a neutron, blue color neutron, red color proton, and there is a neutron which is neutral, which don't have a charge. So here inside the nucleus there is a protons and neutron. Now whatever number of protons are there, that many number of electrons are there in the first orbit, second orbit, and third orbit accordingly, and these are the electrons. These are the electrons marked by the minus sign because they are having negative charge. And this is the entire structure of what your atom. So this is called your atom, atomic structure. So atomic structure consists of nucleus. Nucleus consists of protons and neutrons. Protons are positive charge, neutrons are neutral. To balance the positive charge, negatively charged electrons are there, and that all of you know, this is a basic only. Now, what are semiconductors? So after completing the introduction about the metals and atom, we are going to proceed now about the semiconductors. So what are the semiconductors? So all of you are familiar about the two semiconductor materials, which is called silicon and germanium. So silicon is having atomic number 14 and germanium is having atomic number 32. So look at this diagram very carefully. Silicon's atomic number is 14, and in this diagram only 4 electrons in the valence band. Only 4 electrons in the valence bands are shown. So valence band means outermost shell. And in this case here 32 is the atomic number, but there are only 4 electrons in the outermost shell, that is valence band. And this valence band, outermost shell, is far away from the nuclei because atomic number is large. This valence band is not far away from nuclei because atomic number is small. And now here you can see 14 is the atomic number of silicon. So first orbit, second orbit, and third orbit. In third orbit there are 4 electrons, which is called valence electrons. In case of germanium, you see here 32 is the atomic number. First orbit, second orbit, third orbit, and then fourth orbit. So in fourth orbit, there are 4 electrons. And in this way, in case of silicon and germanium, you remember valence electrons are 4 only. So valency is 4, it is said. Valence electron 4 means electron in the outermost shell are 4. And that's why these two material, silicon and germanium, comes under the category of semiconductor. So now we'll start about the understanding of the basics of semiconductor. So the semiconductor material is the heart of electronics engineering. We cannot think about electronics without semiconductor material. Most electronic devices and components are fabricated by using semiconductor materials. Let us learn about the semiconductor very simply. All of you are using the mobiles, all of you are using the television, and so many electronic instruments and components, laptop, computer, all these are made from semiconductor materials, and the role of semiconductor material is very large in that. The electrical property of a pure semiconductor, silicon and germanium. The electrical property of a pure semiconductor material lies between conductor and insulator material. So this is also all of you know. The conductivity of semiconductor Of course, pure semiconductor, silicon and germanium, lies between conductor and insulator material. At 0 degree Kelvin, which is equal to minus 273 degrees centigrade. This is important, minus 273 degrees centigrade. At 0 degree centigrade, water gets converted into ice and it is minus 273. It is very low. So at 0 degree Kelvin, pure semiconductor, that is silicon and germanium material, behaves like perfect insulator. They do not conduct at all if you put silicon and germanium at minus 273 degrees centigrade. But at higher temperature, means at room temperature, which is 30 degrees centigrade, very large as compared to minus 273, they starts behaving as a conductor. But at higher temperature, the conductivity of semiconductor increases. S means semiconductor. It also works as a good conductor when external voltage. It also works as a good conductor when external voltage, that is electric field, is applied or temperature is increased, and that is the property of semiconductor material. Now, what are the other properties of the semiconductor material? So properties of intrinsic, that is pure semiconductor material, means silicon and germanium, pure silicon and pure germanium. So its valency is 4. So very first property of semiconductor material is what? Valency is 4. What do you mean by valency? Valency means number of electrons present in outermost shell. Number of electrons present in outermost shells. Here 1, 2, 3, 4 valence electrons are there. Here 1, 2, 3 and 4 valence electrons are there. So here again you see 4 valence electrons are shown and 4 valence electrons are shown. So in this way, valency of semiconductor material is what? 4. That is the property number 1. Property number 2 is what? The conductivity of a semiconductor material lies between conductor and insulator. Lies between conductor and insulator. Sometimes means at very low temperature, minus 270 degrees centigrade, they behave as perfect insulator. As temperature increases, they behave as conductor. At 0 degree Kelvin, that is minus 273 degree centigrade, semiconductor material behaves like perfect insulator. So this all of you know. Now here, this is the fourth property. The resistance decreases when we pass more current through semiconductor material. Now when semiconductor material are used in electricity, and when we pass more current through the current through the semiconductor material, the resistance of semiconductor material decreases. Therefore, it has negative temperature coefficient. Or when you heat the semiconductor material, at that time also the resistance of semiconductor material decreases. Its resistance decreases when temperature surrounding to it increased. So resistance of semiconductor material is affected by two parameter. Parameter number 1, temperature surrounding to semiconductor material, and voltage applied to semiconductor material or current flowing through the semiconductor material. More the current flowing, less will be the resistance. So in this way, here these two parameters are very important for this semiconductor material. When resistance is decreased, at that time conductivity is increased. So in case of semiconductor material, resistivity decreases and conductivity increases. This is the property, very important, property number 6. Property number 7, pure silicon passes current in both direction. Because what happens, students get confused. They feel that silicon and germanium are the semiconductor and they do not pass the current in both direction. It is not like that. Pure silicon as well as pure germanium passes current in both direction, and that we are going to study. So here, let us go to this chart now. So this chart is self-explanatory. You can see the chart and you can immediately understand that on this horizontal line, the conductivity is indicated. So here, very low conductivity on left hand side, and on right hand side the conductivity goes on increasing. So very low conductivity is of what? Conductor, good conductor. Gold, silver, copper, iron, aluminium, tungsten, all metals are good conductor of electricity as well as heat. But the conductivity again varies according to atomic number and number of electrons present in outermost shell, that is called valence electrons. Semiconductors conductivity lies between conductor and insulator. In between, silicon, germanium are the examples of semiconductor, and insulators conductivity is very high. So glass, rubber, oil, plastic, diamond, these are the examples of insulator. So insulators does not conduct neither heat nor electricity. So here, now after this, what we are going to study, we are going to revise a 12th standard uh, properties of all these three different materials, semiconductor, conductor and insulator, on the basis of band theory, BAND band. So here see, each material has two bands, namely conduction band and valence band. And the gap between these two bands is called energy gap, is called energy gap and indicated as Eg. As shown as shown below in band diagram, BAND. Band is different and bond is different. So BAND band diagram, the electrons are in valence band, and valence band is also called as your valence shell. And these electrons are knocked out from valence band by applying voltage, that is called your electric energy. So electrons are present in valence band, and below valence band there is one more, there are other bands also which are called field band, FILLED, field bands. Okay, and now today we are going to target only to valence band electrons, because that electrons can be knocked out easily by applying some external electric voltage, or that is called electric energy. The knocked out electrons are called as free electrons in the conduction band. The knocked out electrons are called as free electrons in the conduction band, because when you knock out the electron from outermost shell, that is called valence band, they will come out, and whatever the electrons are knocked out from outermost shell, and when they come out, it is said that electrons are now in conduction band. The state of electrons in between two valence band is nothing but conduction band. So when you knock out the electron from outermost shell of one atom, when you knock out electron from outermost shell of one atom, before the electron gets occupied its position into the outermost shell of neighboring atom, before the electron gets occupied its position into the outermost shell of the neighboring atom, that in between state of the electron is called as conduction band. And that is what we say that the current is flowing, because electron is a charged particle. When it transfers from one location, migrates from one location to another location, it carries charge. So here is that current is nothing but the rate of transfer of electronic charge. Current is nothing but rate of transfer of electronic charge. I is equal to dq by dt. More the rate of transfer of electronic charge through a particular cross section area, more will be the flow of current. More will be the flow of current if the large number of electrons are passing through a particular cross section area. So in this way here, now band diagram, you are familiar with that. So look at this band diagram of metal, semiconductor and insulator. So all of you are aware about this band diagram, and there are two bands basically, valence band and conduction band, and that is what we have mentioned over here. Each material has two bands, namely conduction band and valence band, and the gap between these two band is called energy band gap. Band between these two is called energy band gap. And in this way here, now if you just go to look at this conduction band and valence band, you'll observe that the gap is very large, because this is insulator. So in case of insulator, the energy gap is very large, and therefore it is said that insulators are bad conductor of heat as well as electricity. Let us go to the next, that is called conductor. In conductor, the conduction band and valence band are overlap with each other. Conduction band and valence bands are overlap. Therefore, it is said that in conductor, the electrons present in the outermost shell. Let us take the example of copper. Only one electron is there in the outermost shell of the copper, and therefore it is said that that single electron is electron in the valence band, but it can be very easily detached, and it is said that it is as good as electron in conduction band. Therefore conduction band and these bands are overlap. Now in case of semiconductor, there is a very small gap between valence band and conduction band. Electrons are present in valence band, So let us take the example of silicon and germanium. What is the valency of silicon and germanium? 4. 4 electrons are present in the valence band, and we can easily detach that electrons from valence band to conduction band by applying certain electric energy. And this is the diagram. Now there is one more diagram which will indicate you again there. Conduction band and valence band are overlap with each other. Semiconductor, little bit gap between conduction band and valence band. Electrons are present in valence band. How much amount of voltage electric energy you require to knock out the electron from valence band? 1 electron volt normally it is said. And here it is a 5 electron volt, which is very high. Therefore it is said that they will not conduct with, even though if you apply very high electric energy. And here there is one more diagram which is again explaining you that valence band consists of electrons. E minus means here there are electrons. In every valence band there are electrons. But remember, in case of insulator, the valence band, that is outermost shell, is completely occupied or it is fulfilled. Therefore you cannot detach the electron from outermost shell, and therefore it is said that the insulators are bad conductor of heat and electricity, because the bond is very strong. It cannot be broken. And see here, the valence band and conduction band energy gap is very large. Semiconductor energy gap, band gap, is very small. Electron conductors, the both are overlap, therefore electrons in the valence band are as good as electrons in conduction band. And this diagram is very important for us, because below valence band there is one more band which is showed. It is a filled band, FILLED, filled. And here there is one more concept is introduced, and that concept is of Fermi energy. Concept is of what? Fermi energy. So what is a Fermi energy? Now try to understand from this diagram. In case of conductor, that is metals are good conductor. So here in case of conductors, you can say that conduction band and valence band is occupying each other, means it is overlap. Therefore, whatever number of electrons in the valence band are there, it is almost in the conduction band, almost, because just by connecting the electric voltage, we can knock out that electron. And in this way here, the Fermi energy is very close to the conduction band. The Fermi energy is very close to the conduction band, means you need not to apply any external energy. You need not to apply, or you need not to waste any external energy for the knocking of the electron. You need not to waste energy, any external energy, for knocking out the electron. You need to apply, but you need not to waste the external electric energy applied by you. And therefore it is said that the Fermi level is already very close to the conduction band. Now let us come to the here. In case of semiconductors, the Fermi level is in between conduction band and valence band. Therefore you need to waste some amount of electric energy. You need to waste some amount of electric energy to knock out the electron from valence band and to force into the conduction band. So that is why here there is a band gap, as well as Fermi energy is in between that. Now here, what about insulator? Insulators, see here, the Fermi energy is very close to valence band. Fermi energy is not close to conduction band, it is close to valence band, and therefore it is not possible to knock out the electron from valence band and jump into the conduction band, and that is why the electrons. So here in this diagram, here energy applied to that particular material in the form of electron volt, in the form of electron volt. In case of metal, we need not to apply any, yes, we need not to waste any electric energy in what? Knocking out the electron from valence band. We did not to waste any electric energy to knock out the electron from valence band. Here slight amount of electric energy is wasted. Here, even though if you apply large amount of electric energy, the outermost shell is completely full and occupied and strong bond, so you cannot knock out any electron from valence band. And Fermi energy status indicates the level here. So in case of insulator, Fermi energy is very close to valence band. In case of semiconductor, Fermi energy is exactly at the center of valence band and conduction band. And in case of metal, the Fermi energy is very close to CB, means conduction band. So conduction band and valence bands are overlap to each other. So this is the concept which is very important of the Fermi energy, because this will be required in understanding the light emitting diode and all other electronic applications. Now we'll come to the intrinsic and extrinsic semiconductor. So basically the semiconductor material are classified into two types, intrinsic and extrinsic. What do you mean by intrinsic? So intrinsic semiconductor is nothing but pure semiconductor material such as silicon and germanium without any impurity is called as intrinsic semiconductor. Without any impurity means what? No addition of any other atom is done. So that is very simple. In a pure semiconductor, silicon and germanium, each atom shares 4 valence electrons with 4 neighbor and completes the octet. Now what is the problems here? This paragraph you will understand from the next slide. And to complete the octet, you will require 8 electrons. You will require 8 electrons. And now in case of silicon as well as germanium, the valency is 4. So only 4 electrons are there. So to complete the octet, what the silicon atoms are doing? They are sharing their electron with 4 neighbors. And the 4 neighbor also shares electrons, and therefore upon sharing the octet is completed. But it is not what? It is not a permanent, it is temporary adjustment. It is a temporary adjustment, and because of this sharing, it is said that the formation of covalent bond takes place. So here in a pure semiconductor, silicon as well as germanium, each atom shares 4 valence electrons with 4 neighbor and complete the octet. Now here see, due to sharing of electrons, the covalent bond is formed, and these covalent bonds between neighboring atoms are weak bonds because sharing is there. So it is a weak bond. Therefore, covalent bond can be easily broken by applying external electric field, that is called voltage. By applying external voltage, that is the electric field, or when temperature of semiconductor material is increased, at that time also you can break the covalent bonds. So you can stop the slide, you can read it again. Now here, when covalent bonds are broken, either by applying voltage, that is external electric field, or either by increasing the temperature surrounding two semiconductor material, at that time electrons are knocked out from valence band and they jump into conduction band and current starts flowing. So when the electrons are knocked out from valence band, they jump into conduction band and current starts flowing. Now here, as shown below, the atomic number of silicon is 14. So we have already seen that earlier, but here again we are going to show you. And the number of electrons in outermost shell, that is valence electrons, are 4. Therefore, each atom shares 4 valence electrons with the 4 neighbor and completes the octet. So completing octet is very important in case of semiconductor material silicon. So here what is happening here now? Look at the diagram very carefully. So this is your silicon. So this is the silicon atom. Now this silicon atom is having 1, 2, 3 and 4 electrons, and these 4 electron belongs to this central silicon atom. And there is one more silicon atom on the right hand side. There is one more silicon atom on the left hand side. There is one more silicon atom on top of this silicon, and there is one more silicon atom at the bottom of this silicon. Each silicon atom you see here, there are 4 electrons, and these are called valence electron. This also silicon atom is having how many electrons? 1, 2, 3 and 4. And what is happening now? All silicon atoms are sharing their electrons with the neighbor. The center one is sharing its 4 electrons with all 4 neighbor. One is on the right hand side, one is on left hand side, one is on the top, one is at the bottom. Now here there is a structure. Now this silicon also will share. Here there is atom on the top and on the left hand side, and the bottom is here, this one. And in this way here, upon sharing, complete covalent bond or covalent bond formation takes place. Upon sharing, covalent bond formation takes place, and this is the structure. So it is given silicon intrinsic semiconductor, and this I have taken from electronic desk. Thanks to electronic desk for giving very nice diagram this. So here, this is again one more diagram. You can see atomic structure. This in the beginning I have shown you silicon and 4 valence electrons are there. 14 is the atomic number, and here see
center silicon atom, there are having 1 2 3 4 electrons for this atom, and here this silicon atom 1 2 3 and 4, these four are from this, and this silicon sharing, yes, 4 electrons with the 4 neighbor, and neighbor also shares their electron with this center atom, and formation of what takes place, covalent bond. Now when you take a semiconductor material, and apply electric energy, that is voltage, at that time what happens, when you take a semiconductor material here, silicon, and this silicon atom is sharing its electron with the 4 neighbor, and therefore sharing of the electron, due to sharing of electron with 4 neighbor, covalent bond is formed. Now when you take a semiconductor material, this square box is having a semiconductor material, and when you apply the electric energy, at that time, because of this electric potential, that is the voltage of the battery, the electron starts flowing from negative to the positive, but our conventional direction is from positive to negative, and this electric voltage of the battery is used to break the covalent bond. This electric voltage of the battery is used to break the covalent bond, and when the bonds are broken, the electrons in the outermost shell, that is called valence shell, are knocked out, are and therefore it is said that this electric energy, that is the voltage, is must, and some part of this electric energy or voltage is wasted in breaking covalent bond. Some part of this electric energy is wasted in breaking covalent bond, and then current starts flowing. Without breaking covalent bond, you cannot knock out the electron, and therefore it is said that some amount of electric energy is wasted. And in this way here, if you connect the battery like this, the electrons will flow actually from negative to positive, but conventional is positive to negative. But if you connect the battery like this again, no matter the way which battery is connected, semiconductor, silicon or germanium passes current in both direction, because only the target is to break the covalent bond by using electric energy, that is the voltage of this battery. So if you connect the battery like this, the current will flow positive to negative, conventional, negative to positive, actual flow of electron. So here this diagram I have given intentionally because it is to be understood that how does the current flows. After breaking the covalent bond, only the current will flow, and that's why it is said some amount of electric energy is wasted. Now, as shown in above, intrinsic semiconductor material conducts in both direction, but the electrons are made free after breaking the covalent bond, and small amount of energy is required to break the covalent bond at low temperature. At high temperature, very less amount of electric energy is required, because electrons are thermally excited due to the high temperature only, and due to thermal excitation you don't require much more electric energy. Therefore, the conductivity of this semiconductor material is increased by doping. Now, what is the problem? Problem with pure semiconductor is we need to break the covalent bond. We need to break the covalent bond, and after breaking the covalent bond only, what happens? The current starts flowing. So here, that amount of energy which is required to break the covalent bond, if you want to save, then you are doing one logic, you are applying one logic of what, therefore the conductivity of this semiconductor material, that is pure semiconductor material, is increased by doping. Doping means what? Adding the pentavalent or trivalent impurity, and we fabricate the extrinsic semiconductor material, and they are classified as n type and p type. So to increase the conductivity of a pure silicon and germanium, we are going to adopt a method of doping. Doping means adding a trivalent impurity or pentavalent impurity into pure semiconductor material, which is called intrinsic semiconductor material. And now we'll study how to fabricate extrinsic semiconductor material. Of course, extrinsic semiconductor material is fabricated from intrinsic only by adding trivalent or pentavalent impurity into that. So extrinsic semiconductor material is called n-type and p-type. So here see, the semiconductors doped by suitable impurity is called extrinsic semiconductor. The semiconductor doped by suitable impurity, trivalent or pentavalent, is called extrinsic. And there are two types of extrinsic semiconductors. So number one, N-type extrinsic semiconductor, and number two, P-type extrinsic semiconductor. When you fabricate N-type semiconductor material, the semiconductors doped by pentavalent atom. The semiconductors doped by pentavalent atom. And when you fabricate a P-type, the semiconductors are doped by trivalent atom. And let us see, it is very simple. It's a simple revision through the frame of reference of electronic science. N-type semiconductor. The conductivity of intrinsic, that is pure semiconductor, is increased by adding pentavalent impurity, which is called donor, into intrinsic semiconductor, that is pure semiconductor. So extrinsic semiconductors are fabricated by using intrinsic semiconductor only. So the conductivity of intrinsic semiconductor is increased by adding pentavalent impurity. This process of adding pentavalent impurity, that is called donor, to intrinsic semiconductor atom is called doping. Is called doping. Due to doping of pentavalent impurity, more free electrons are created in N-type semiconductor material. Semiconductor, SC means semiconductor material. And we'll see that slide. So here, this is very important now here. This center atom, earlier it was silicon. Now, in that structure of the silicon, pure silicon, we have added one atom of pentavalent impurity, and this P stands for phosphorus. This P stands for phosphorus. So when we add a pentavalent impurity, what do you mean by pentavalent impurity? The name itself will communicate you that pentavalent, penta means five. Five valence electrons are there. That's why it is said pentavalent. Penta means five, valent means valency. The valency is five. And therefore here when you add that atom, one atom of that phosphorus, that is a pentavalent impurity, into the silicon structure, see here what happens. This phosphorus atom shares four electrons with four neighbor of the silicon, and one electron remains extra because it is having five electron, and this is called free electron, and again here this again shares electron, therefore there is a formation of what bond? Covalent bond only. But now here there is already one extra electron, that is a free electron. And in this way, if you add one atom of the phosphorus, that is pentavalent impurity, one free electron is created. And suppose the structure is very big, and if you add 10 atom, 100 atom, 20, 200 atoms, then you are going to create that many free electrons. And this is what it is very clearly given here. Si, intrinsic semiconductor atom, silicon. P, pentavalent impurity atom, means that is a phosphorus example. And here, as shown in above, one pentavalent impurity of phosphorus atom is added into intrinsic semiconductor. Pentavalent impurity atom have 5 electrons in its outermost shell, and these electrons are called as valence electron. Valence is 5. Therefore, this atom shares 4 electrons with 4 silicon atom, and one excess electron is called as free electron. In this way, one atom of pentavalent impurity creates one free electron, and formation of N-type semiconductor material take place. So in this way, what you have done? You have added one atom of pentavalent impurity and created one free electron, and that free electron now can be easily detached. Electron is free now. Electron is free, and that can be easily detached just by connecting the battery. You need not to waste electric energy of your electric voltage source, and that is why it is said the conductivity of N-type semiconductor material is greater than pure silicon or germanium, that is intrinsic semiconductor material. And now what are the properties here? The properties of N-type semiconductor material. Electrons are majority charge carriers in N-type semiconductor material. Electrons are majority charge carriers. Means what? Means flow of current is due to repulsive force between electrons. So when you take N-type material and when you connect the battery, the free electron will be pushed by the negative terminal of the battery towards the positive terminal of the battery, because negative terminal of the battery is also source of electron. this electron, this free electron and that electron will repel from each other. That is repulsive force. And that electron will be pushed towards the positive terminal of the battery. That is called, yes, repulsion force between electrons. Current flows. Current means electron. We have studied that rate of flow of, yes, charge. Rate of flow of charge, that is rate of flow of electron, is nothing but current. So here current flows, that is electron, by the process of drift, drift. Drift means what? There is a repulsive force between electron, and that repulsive force between electron is called drift only. Due to drift, an electron requires less time to travel. Due to drift, an electron requires less time to travel. Travel from where to where? Positive of the battery to negative of the battery through semiconductor material, that is N-type. And that diagram I am going to show you. So here, due to drift, the electron requires less time to travel, and resistance of N-type semiconductor material is also very less. So in this way, that property is very important. I'm going to explain you once again in the diagram. The number of free electron depends on doping level of pentavalent impurity. So one atom, if you if you add 10 atom of the pentavalent impurity, 10 free electrons, 100 atom pentavalent impurity, 100 free electrons, and that's number of atom. If you add more and more, that is called doping. So there is a lightly doped, moderately doped, and heavily doped. In heavily doped, large number of pentavalent atoms are added. In moderately doped, small number of pentavalent atoms are added, and in lightly doped, very less atoms of pentavalent impurity are added. And here, see, I am going to show you one structure. Here, one pentavalent atom, one free electron. Second pentavalent atom, second free electron. Third pentavalent atom, third free electron. And in this way, you will understand that here three pentavalent atoms are added, therefore three free electrons are created. And that is what here it is said, that number of free electron depends on doping level of pentavalent impurity, lightly, moderately, and heavily. Now let us go to the next, that is called p-type semiconductor material. The conductivity of intrinsic, that is pure semiconductor. Intrinsic semiconductor is increased by adding trivalent impurity. So not a pentavalent, that is a trivalent impurity. So trivalent, by adding trivalent impurity, just a minute, I'll check this one. Very simple. Uh, p-type semiconductor material. In that, by adding a trivalent, not a pentavalent, that is a trivalent, that is called your acceptor, into intrinsic semiconductor material, that is a pure semiconductor material, p-type semiconductor. The conductivity of intrinsic semiconductor material is increased by adding trivalent impurity into intrinsic semiconductor, that is this thing here. Now here, this process of adding the trivalent impurity, see here now, this again, here there will be a small change. The process of adding trivalent impurity into intrinsic material is called, here there is a trivalent. So here there is a trivalent impurity. The process of adding trivalent into intrinsic semiconductor material is called as doping. Due to doping of trivalent impurity, more free electrons are created in N-type semiconductor material. So in this way here, due to doping, more uh, holes are created in that type of material, and we'll see that. Now see here, in silicon structure, in what? Silicon structure, aluminium is added. Aluminium is what? Trivalent impurity. Now what is a trivalent impurity? Trivalent impurity is nothing but an impurity which is having, tri means three valence electrons. How many? Three valence electrons. Therefore this aluminium atom will share one electron, second electron, third electron with three neighbor. With how many neighbor? Three neighbor. And in this way here, there is no electron to share with fourth silicon atom. There is no electron to share with what? Fourth silicon atom, and that vacancy of electron or that shortage of electron is called hole, that is called presence of hole. And this bond is incomplete covalent bond. This bond is what? Incomplete covalent bond, and this is a complete covalent bond. That is also weak in the nature. That is also weak in the nature. And see here, this is very important now. One atom of the aluminum, that is trivalent impurity, creates one hole. Now what is hole? Hole is the vacancy of the electron. There is no electron, fourth electron with aluminum atom to share with this silicon atom. And that non-availability of the electron, that less electron is shown as hole, and that is the creation of hole. So here see, as shown above, one trivalent impurity of aluminum atom is added into intrinsic semiconductor. As shown above, one trivalent impurity of aluminum is added into intrinsic semiconductor. Trivalent impurity atoms have 3 electrons in its outermost shell, and these electrons are called as valence electron, and therefore it is said that valence is 3. Trivalent impurity atoms valency is 3. 3 electrons are there. So here, therefore, this atom shares only 3 electrons with 3 silicon atom. Therefore, this atom shares only 3 electrons with 3 silicon atoms, and 1 electron is short, that is called less. That is less, and this is a vacancy of electron which is indicated as a hole. And this is a vacancy of electron which is indicated as a hole. So hole is not anything special, it is a vacancy of electron. In this way, one atom of trivalent impurity creates one hole, and formation of p-type semiconductor material takes place. Hole is nothing but vacancy of electron. And hole is imaginary concept. Hole is what? Imaginary concept. We imagine that there is a vacancy of electron, and that vacancy of electron we called as a hole. So it is an imaginary concept, and it is treated as a positive charge always we indicate hole as a positive charge, because any other electron which gets attracted towards this structure then what will happen? That electron will occupy into that hole. Hole is nothing but vacancy, that is an imaginary concept, and it is treated as a positive charge because any other electron which gets attracted towards this structure occupies the position into the hole. That electron will sit into the hole and will complete that structure. In this way, there is a gain of electron, therefore this hole is treated as positive charge. In this way, there is a gain of electron, therefore it is treated as a positive charge. Now we'll compare hole with proton. Proton are also positive charge, but proton are having mass. Proton possesses some mass, and they exist, whereas hole is a vacancy of electron, that is imaginary concept. And this is very important to remember, the difference between proton and hole, which we treat as a positive charge carrier. So in this way here, this is a formation of p-type material. And what are the properties of p-type semiconductor, that also you see, it's also very important. In p-type semiconductor material, holes are majority charge carrier. Means what? That is, holes are carrier of electrons. And flow of current is due to recombination of electron and hole. And flow of current is due to recombination of electron and hole, because when you connect a battery to this structure, then electron are supplied by the negative terminal of the battery. That electron will come and occupy the position in this hole, but immediately the next electron supplied by the battery will come, and that will knock out this electron. And in this way, the electron supplied by the battery cannot occupy the position into the hole for a long time, because there will be continuous electron supplied by the negative of the battery, and in this way here this hole becomes carrier of electron. Hole becomes carrier of the electron because electron will occupy the position into the hole, and then only it will be knocked out by the next incoming electron. And therefore it is said, in case of p-type material, the flow of electron is by the process of diffusion. Diffusion means what? Electron will diffuse, means will occupy the position into the hole, and then it will come out. So that also we are going to study, and that is also important property of this here. So here the protons, you understood, and now property of p-type semiconductor material. The holes are majority charge carrier, that is, holes are carrier of electrons, and flow of current is due to recombination of electron and hole. Recombination of electron and hole is more important. The current flows, that is electron. Current means what? Rate of flow of charge. And who is carrying the charge? Electron is a charge particle. It is carrying the charge. The current flows, that is electron, by the process of diffusion of electron into hole. By the process of diffusion of electron into hole. Due to diffusion, electron requires more time to travel, and resistance of p-type semiconductor material is more. And resistance of p-type semiconductor is more because each and every electron first of all diffuse into the hole and then it comes out. Like that, if you imagine 100 holes are there, then 100 electrons at a time diffuse into 100 holes, and they will come out from the hole. Therefore, it is said that more time will be required to electron to travel from negative of the battery to the positive of battery through p-type material. Through p-type material. Whereas in n-type material, less time will be required because electrons are not diffused into the holes. In n-type material, there are free electrons only. Repulsive force is there. Therefore, n-type material's conductivity is very high as compared to p-type. The number of holes depends on doping level of trivalent impurity. Again, same, lightly doped, moderately doped, heavily doped. How many holes you can create, that depends on how many trivalent impurity you have added. And here I have shown you the three holes creation. One aluminum atom, second aluminum atom, third aluminum atom. If you add three aluminum atom in this structure, see here there is one hole, vacancy of electron, one more hole, and one more hole. So like that, it is very simple. And here this diagram is there, you can easily understand silicon, 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 and here it is a Pb, and here it is called donor impurity, means n-type formation, means here this is a pentavalent atom added, so it is sharing 4 electron, and fifth electron you see here, it is here. So this is a free electron. So fifth excess electron is here. And like that only, if you take 4 silicon, 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 and if you add a trivalent atom, then here there is a hot hole. You can see a red. So here this vacancy of electron. So here there are, see, 1, 2, 3, 4, 5, 6, 7, 8. So here 8 are from where? 1 from all 4 silicon. This silicon's 1, this silicon's 1, this silicon 1, this silicon 1, and 4 from this pentavalent impurity. One is excess of the pentavalent impurity, that is free. And here 1, 2, 3, 4, 5, 6, 7, and eighth one is not there because it is having only 3 electrons, because it is a trivalent impurity atom, and therefore this is called hole, and this is p-type material. So now this is important here. See, n-type and p-type semiconductor material passes current in both direction, because after understanding all these things, n-type semiconductor material are having large number of free electron, E minus, E minus, E minus means electrons with negative charge. And when you connect the battery like this, conventional direction of flow of current is from positive to negative. Conventional direction of flow of current is positive to negative. Actual electron flows from negative to positive. So when this electron enters here, supplied by the negative of the battery, that electron pushes this electron towards the positive of the battery, and that is called repulsive force between electron. And here it takes very less time to what, go from negative of the battery to positive of the battery. If you reverse the polarity, positive here and negative here, electron will enter in this direction and will come like that. So that is the actual direction of flow of electron, and this is the conventional direction of flow of current, you can say. Now here p-type material, In p-type material, there is a positive means hole. The holes are more marked as a positive, plus means hole. There are so many holes. Now if you connect the battery like this, conventional direction of flow of current is positive negative, but electron will enter from negative of the material of the battery like this, and they will occupy the position into the hole. But as soon as that electron occupies the position into hole, next electron will enter, and that will knock out that electron, and in this way each electron will diffuse into the hole, and then it will get travel towards the positive of the battery, and therefore it is said that electron diffuse into the hole and formation of electron hole pair combination takes place, and therefore here electron will take more time to travel from negative of the battery to the positive of the battery. If you reverse the battery, then here negative terminal is there. The electron supplied by the battery is from negative terminal. They will enter in this way, and that electron will occupy into the position of the hole. But the next incoming electron from negative of the battery will not allow that electron to occupy the position into the hole for a long time. It will knock that electron, and then that electron will jump into the next hole like that. The electron will take more time to travel in p-type material because it has to diffuse into the number of holes. It has to diffuse into the number of holes, and therefore it is said p-type semiconductor material is having very large resistance as compared to n-type semiconductor material. But conductivity is increased, because in this case, as soon as the battery you connect, or in this case as soon as you connect the battery, the current starts flowing. You need not to break the covalent bond like in pure silicon and germanium. You need not to break the covalent bond like in pure silicon and germanium, and that is why it is said n-type material and p-type material are having a very good conductivity as compared to pure silicon and germanium. That's why we have said that the conductivity of intrinsic semiconductor material, that is pure semiconductor material, is increased by doping, means adding trivalent impurity or pentavalent impurity, and fabrication of n-type and p-type material. So here see, as shown above, both extrinsic semiconductor p-type and n-type conducts in both direction. So here if you reverse the battery, current will go in other direction also, because when we combine p-type to n-type in the next lecture, the formation of p-n junction diode takes place, and it will not allow to flow the current in reverse direction. Therefore this is important. As shown in above, the both extrinsic semiconductor material p-type and n-type conducts in both direction. In case of n-type semiconductor, the electrons are majority charge carriers, and in case of p-type semiconductor, the holes are majority charge carriers. So this we have already elaborated. The flow of current, that is electron, in n-type semiconductor material is by drift means what? Repulsive force between electrons. The flow of current, that is electron, in p-type semiconductor material is by diffusion. Diffusion means what? Recombination of electron and hole. Electron has to diffuse into the hole, and therefore it is also said that called as electron hole pair, EHP. And this is all about your 12th standard basic, which we have covered, because in 12th standard this this much what you can say details are not covered through the frame of reference of electronic science. That's why we have revised your metals, then your valence band, conduction band, what do you mean by the atom, what do you mean by the proton, neutron, and all atomic atoms structure of the atom, then formation of what, fabrication of n-type material, fabrication of p-type material, then pure semiconductor silicon, why the silicon is having a less conductivity as compared to n-type and p-type. All that we have covered, and this you go through the different slides. You can stop the slide, you can read it again, because this is very much helpful and important through the frame of reference of electronic science. And in the next lecture, we'll combine p-type material with n-type material, and then fabrication of p-n junction diode takes place, which will not allow to flow the current in reverse direction. But remember, pure silicon germanium, p-type material, n-type material passes current in both direction. So thank you very much for watching the video. Thanks.